and welcome to a research series of presentations. Today we have Catherine Shaver back for an encore presentation. This year, July 14th, I did overview of statistical applications part 1, which was very well received. And our PowerPoint and our video from that presentation are there on our website if you want to go back and review that, as will this one be in the next week or so. So today Catherine is back with us to do part 2 of statistical applications, and we're very glad you could make it. Thank you.
Glad to be here.
Reminder, please be sure you sign in, and if you want to receive CME credit, there's an evaluation form in the back. You need to fill that out and sign at the bottom. Regardless of whether you want the credit, we hope you'll give us your feedback by using the evaluation form. And then I'll mention while I'm up here that after today, our next presentation in this series will be on Tuesday, November 10th, when Chuck Hite will be with us to talk about the IRB process and research evidence. So, Catherine, thank you again for coming.
All right, thank you. Okay, so just to make sure, were you guys all here last time? But okay, I'll give you a pass. That's okay. The objectives obviously are the same as they were last time. So we'll skip on over that. In part 1, we talked about descriptive statistics. We talked about types of data, variables, independent versus dependent variables. And then we got started on a few different statistical techniques, pretty much the 3 kinds of t-tests. And that's where we stopped. So today we're going to go a little more deeply into some other statistical techniques, honestly ones that are probably used more frequently in what I see here at Carilion, and then also talk about power analysis. So as we go through each of the techniques, we'll have kind of a consistent format of example research questions, and then what your data would look like, and then some detail about the statistical technique that's appropriate for that question and type of data. So the first thing, again, kind of segueing from talking about t-tests last time into talking about analysis of variance this time. So t-test, if you remember, was to compare if you have 2 groups and you want to compare the means of those 2 groups. Well, what do you do if you have more than 2 groups? That's when you turn to analysis of variance. And so it's kind of an extension of a t-test in its simplest form, and is used when you may have one independent variable with 3 or more levels, so a grouping variable that puts people into 3 or more groups. You may also have more than one independent variable. That's a possibility as well, and that's the kind of example that we're going to be looking at here. So our question is, do diet type and gender affect LDL levels? And in this case, diet type and gender are our 2 independent variables. And there's a little bit of notation here. So this is called a 2x3 factorial ANOVA. And what that means is we have 2 variables, 2 not because this is the number 2, just because there's a place here and a place after the by, the x. If we had 3 independent variables, we would have another x and another number. So it's how many numbers you have in that notation tells you how many independent variables you have. What this number actually is tells you how many levels that variable has. So 2x3 means we have gender with 2 levels and diet with 3 levels. If diet had 4 levels, it would be 2x4. So I should say this is a totally made up, contrived example. I don't think it's physiologically possible for things to turn out the way I've made them turn out here. But this is just for teaching purposes. So this is an example of what your data might look like in a spreadsheet. Again, remembering that each row in your database is going to be a different person. You have your ID number over here, and then we have gender, just coded as male or female, the diet type, no fat, low fat, or high fat, and then a measure of the LDL. So when you do an analysis of variance, you're looking for a couple of different things. In a case like this where you have more than one independent variable, you're looking for what's called the main effect of each independent variable. So if you're just looking at gender by itself and wondering if it has an effect on LDL, that's the main effect of gender. And then similarly for diet, if you just want to know if diet by itself makes a difference, that's the main effect of diet. So as you can see here, the means for males and females are pretty similar, right? So there's not, even though I don't have actual output or results here, we can assume that there's not a statistically significant difference in LDL based on gender. So no main effect, how you would say that there's no main effect of gender on LDL. Diet, however, looks like there might be something going on. Probably no fat looks to be a good bit lower than low or high fat. That difference between low and high is probably not big enough to be statistically significant, but I would suspect that this one is, so there probably is a main effect of diet here. But what's often more interesting in a factorial analysis of variance is the interaction. And often, sometimes the easiest way to pick up on an interaction is through a graph like this. So whenever, excuse me, whenever your lines cross, that signifies that you're dealing with an interaction. And that can usually be a pretty exciting finding because sometimes it may be something that was unexpected that you're not necessarily looking for. So when you see these cross lines, you know that's going to give you something interesting to talk about. I remember doing some last minute graph making on the hotel room floor in Chicago for a conference one time when I was in graduate school, and I had an interaction that I was frantically trying to figure out and describe, but that's exciting when you have something like that going on. So again, this is totally made up, but let's take this apart a little bit and see what's going on here. So we have LDL on the y-axis, we have gender on the x-axis, and then our three different lines represent the different diet conditions. So this blue line signifies the no-fat diet, and basically between male and female the levels of LDL were the same. So there's really nothing interesting here. But what's going on here, the red line is low fat and the green line is high fat. So what we're seeing is that the low fat diet led to lower LDL in males but higher in females, whereas the high fat diet led to higher LDLs in males and lower LDLs in females. So we would say that the effect of diet is different for men and women. That's the nature of the interaction. And again, obviously, there's no reality in this. But that's kind of how you take that apart and interpret that. And again, if you're not expecting it, it can be pretty interesting sometimes what you may uncover. So that is not, I don't do a lot of ANOVAs because most of the data we work with just doesn't lend itself to that very often. We're usually not, we don't do a lot of controlled, randomized type studies at this point anyway. So I've never worked on anything where people were assigned into 3 groups or more. And it's just not a technique by it's just alone like that usually fits with a lot of what we do. So kind of moving away from that, I want to spend a little time talking about correlation. Correlation is, excuse me, not going to be the primary statistical technique that you would use in a study. By itself, it's not very strong. But I think because sometimes it's misinterpreted or maybe not well understood and the word correlation gets thrown around a lot, I just want to take a little time to go over what it actually is, what it can do, and what it can't do. So it's used to examine the linear relationships between two continuous variables. So again, last time we talked about continuous versus categorical data. So if you have categorical data, that won't apply to at least this type of correlation that we're talking about here. So our example question might be, what is the relationship between dietary cholesterol intake and LDL? So both of those are going to be measured as continuous variables. So a little bit about the correlation coefficient. It's actually, this is Pearson's correlation coefficient, or Pearson's R. It ranges from -1 to +1. And a couple things about it are important. So the number and the sign mean different things. So the number tells us about the strength of the relationship. If the values are closer to +1 or -1, then it means the relationship is stronger. A value of 0 would mean no relationship at all, and values right around 0, either positive or negative, would mean a weak or nearly non-existent relationship. The sign tells us something about the nature of that relationship. So if the correlation is positive, it means that we have a direct relationship. If it's negative, it means we have an inverse relationship. And the next slide tells you a little bit more about that in detail. So if you have, this is an example, or this is sort of a demonstration of a positive relationship. So as the value of one variable increases, the other one increases, or as it goes down, the other one goes down. They move in the same direction, and that's a positive correlation. If the correlation is negative, then you have the situation where as one variable goes up, the other one goes down. And so those are the two types of relationships that we can identify with correlation. And it's always important to remember that correlation does not equal causation. And you hopefully have heard that before. You'll probably hear it again. So just because two things are correlated doesn't mean that one causes the other. It can be tempting, especially if there is, if time or chronology enters into it such that one of the things you're measuring happened before the other. It's tempting to assume that that one caused the other. But there's nothing about the technique of correlation that gives you the ability to do that. One example, just kind of off the top of my head, is that there's a correlation between ice cream sales and drowning. And so if you assume some causality there, you might think something about eating ice cream is causing people to drown when they swim, right? But it's actually a third variable. It's the time of year. So in summer, more ice cream is sold and more people are swimming, so the odds of somebody drowning, I guess, are greater at that time of the year than in the winter. So there are a lot of things that can explain a correlational relationship, but always be careful about making that assumption that one thing causes the other. So this is kind of what your data would look like for correlation, just very straightforward. You have the cholesterol measurement and the LDL for each person, and then you just basically run your correlation on this. And these made-up data are such that the value of R was a positive 0.94. You almost never in real life see a correlation that high. If you did, it would be something to get pretty excited about. And so this indicates that there's a very strong relationship between the cholesterol intake and LDL. Okay, so this is really where I want to spend. Oh, yep, go ahead.
For Pearson coefficient, what is considered like significant? I know I've seen like 0.8, pretty good. 60 average is pretty good.
It depends. That's a good question. It depends On a couple things. So statistically significant is going to depend a lot on your sample size and on the variability of the data. So it is possible to get a low correlation, what we would think of as a weak correlation, that is statistically significant. If you have a large enough sample, that can happen. So you might see 0.2, 0.3 be statistically significant. So hold that thought just a second. Typically, anything above about 0.8 is considered strong, very strong, I guess. 6, 0.7 would be, I guess, strong, and then 0.4, 0.5 is kind of moderate. So I would say anything above 0.4 or 0.5 would get my interest, and it would probably be, I mean, you're not going to have a correlation of 0.8 that's not statistically significant. So that's on that end, you're going to be okay. Where you need to watch out, and why this is not, a powerful technique all by itself, is on the lower end of things. When you do get those correlations of 0.2 that are statistically significant, you have to kind of stop and say, but should I really be getting excited about this? Because this is not really that strong of a relationship. So I would, I guess, keep that in mind. Probably 0.2 to 0.3, I would say, is weak. Maybe 0.2, very weak. There, if you Googled, you could find, probably a little explanatory thing of basically what I just said. But yeah, so just watch out for low correlations that are statistically significant, and remember that that's not maybe all that clinically meaningful. Thanks, that was a good question. Okay, so this is where I want to spend kind of more time, because this is what I see a lot of here at Carilion, categorical data of some sort or the other. So far we've talked about, with t-tests, analysis of variance, and correlation, we've talked about situations where our data were continuous, right? But what do we do if we have categorical data? And we know that happens. Mortality is the first example that jumps off the top of my head. Obviously, there are certain things in healthcare that we're interested in that are yes-no type of variables. So two techniques that we'll talk about today are chi-square and logistic regression. And I would say these two things probably make up maybe 60 or 70% of my work, probably in the end. These are more common than some of the other things we've discussed. So chi-square, or Fisher's exact test, is applicable when your predictor variable, your independent variable, and your outcome are both categorical. So you might, again, with categorical, we're talking about things like mortality, yes, no. Did they get a certain test? Yes, no. Did they get a certain drug? Yes, no. Did they have a certain complication? Yes, no. It can also have more than two categories. That is possible. We won't look at that in detail here, but sometimes there are instances where there's a categorical variable that has 3 values, or maybe 4. When people sometimes want to analyze things that have like 7 or 8 categories, and I usually try to sort of shy away from that because it gets real complicated, especially if you have a small sample size. So usually 2 is kind of the most common. And what this actually ends up being, and to sort of say things another way here, is what we're doing is comparing two proportions, comparing proportions in two groups. So, what was the proportion that died in this group versus in this group? And so you can use a chi-square or Fisher's exact test, or actually some other tests that we won't talk about, to compare these proportions. So before we had all of the computer technology that we have now, people had to do their statistics by hand. And I guess I'm old enough to have done a little bit of that. I never had to do punch cards, so I can't really complain. But I did have to do some of these things by hand when I was learning. And my students that have had me at Jefferson College can tell you that I like to make them do things by hand too, which they don't always appreciate. But so chi-square is extremely easy to do by hand. It's one of the easiest tests to do the calculations. They're fairly straightforward. And so it became very popular before we had computers to help us out. Sometimes it was probably overused or kind of geared, the research that was done was kind of geared towards what statistical test you could do that wouldn't take a ream of paper and 3 weeks to do all those calculations. But it doesn't work well when you have a small sample size or if you have sparse data. So if you have a 2x2 table and one cell of that table doesn't have very many people in it, then that poses a problem for the chi-square. So Fisher's exact test is a technique that just takes advantage of computational power, basically, to give you an alternative to the chi-square when you're doing this kind of test. So it's basically doing the same thing. You can report either one. But definitely when you have a situation of a small sample size, the Fisher's exact test kind of bails you out and lets you carry on with what the chi-square would stop you from doing. And we'll see that in just a minute.
So is there kind of a guide or a cut point at which you could go to the other one to the other?
We'll get to it here in a couple more slides, but the statistical programs take care of that for you, which is nice. You don't have to decide ahead of time what you're going to do. It gives you warnings, and then you use what you need to use based on what kind of warnings it throws up. Okay, so this is an actual question. Megan will recognize this, that has not been answered yet. I borrowed this from a pharmacy resident research project that's just getting started. As an example, where we're going to be comparing two proportions. So they're asking whether patients with Staph aureus who receive infectious disease consult have a lower 60-day mortality compared to those patients who don't receive that ID consult. And don't tell them the data are totally, I had to really do a lot of making things up, so the ID docs would be real excited to see what I've made up here, because it makes them very valuable. So this is just like all the others. Basically, each row is an individual patient. We just have coded here whether or not they received an ID consult, and then, are they alive at 60 days, yes or no. So this is taken actually from SAS. This is SAS output, kind of what it looks like, or at least sort of what it looks like put into a PowerPoint slide and made bigger. But what you see here is, so there's more things in here, but this is essentially the 2x2 table. You have, were they alive at 60 days, yes or no? Did they receive a consult, yes, no? And then these are the numbers in each of those cells. And then below that, we have the percentages, which, well, we can talk about that a little bit, because actually this turns out to be helpful in interpreting these tables. So I'll come back to that in just a second. This is the statistical, this is sort of the next part of the output. This is all the different statistical tests that are run. And I've put in red the things that you would want to focus on here. I don't usually use any of this other stuff. And down here I don't usually use any of these other things. So these are kind of the three places my eyes go when I'm doing one of these analyses. So I look at my chi-square, and this column is the p-value. So assuming I'm using 0.05 as my cutoff, I say, oh, look, 0.02, I have significant relationship here between, this means there's a significant association between receiving an ID consult and mortality. But then I go on down a little bit and I see this warning, and it's telling me, this is sort of a complicated way of telling me that the data in my 2x2 table, that the cells are sparse and my sample size is small, is basically what this means. It will give you, sometimes it'll say 50% of the cells have expected counts less than 5. But basically, anytime it puts up this warning and says that chi-square may not be valid, that's when then my eyes go on down here to the table with Fisher's exact test. So that answers your question about how to know which to use. Now, I'm not sure what SPSS does as far as giving you that warning, but it's probably pretty, I would assume it works the same way. Does it? Yeah, okay. So when I go down here, I want to look at the two-sided probability. There might be times when you would want to look at either of these one-sided, but I'm going to stick with the two-sided for now. So this would be my p-value associated with that two-sided Fisher's exact test. And you see, actually, it's 0.08. As I was fiddling around with these data, kind of trying to manufacture the results, I thought, well, so if you remember, I made it so that there was only one person who lived in the group that got an ID consult. And I could have made it none so that we wouldn't have had that 0.08, and then we could have just breezed on by that and whatever. But I decided to leave it alone because it actually illustrates. I didn't want to get any more totally unrealistic than I was with the data. And it illustrates an interesting difference between the regular chi-square and the Fisher's exact test. So basically, what you're seeing here, just by comparing the p-values, you can see that Fisher's exact test is more stringent or more conservative, I guess, but really what you would say is it's more, I guess, accurate. By those exact computational methods, you're actually arriving at a different conclusion than you would if you had ignored this warning and used your p-value up here. You would have said there's a significant relationship. Whereas here you'd have to say, what I would say here is there's a trend, and probably if I had more data, it would be statistically significant below the 0.05 level. So a sample size of 12 is pretty small for doing something like this. So that's why if you had similar patterns in a larger data set, it would be significant with no problem. But I thought it was kind of interesting how this shows you the difference a little bit in the two ways of calculating the value and calculating the significance, and why it's important to use Fisher's exact test when you have that small sample or sparse cells, because it actually does make a difference. Okay, so before we go on, any more questions about this? This is, again, just very common in terms of a lot of the questions that people ask. Usually, a lot of times boil down to comparing two proportions. And there are some other things we can do. There are confidence intervals and things like that. But I didn't want to take the time to go into all of that today. Okay, so I was saying earlier that I had reworked this presentation just a little bit. This is actually the first time I've put logistic regression in here, because when I first started teaching this course a number of years ago, it wasn't common really at all. And I rearranged things, but I used to go from talking about correlation into talking about linear regression and multiple linear regression, which is having an outcome variable that is continuous. But I have seen over the years that again, hardly ever happens here with our kind of data and the kind of questions that we ask. It's much more common for people to be studying an outcome that is binary, like a yes-no type of an outcome, again, like mortality or complications or, I don't know, I'm sure you can think of things from your own areas and your own interests that have a binary outcome. So I thought it made more sense to talk about logistic regression because it's so much more popular than to talk about just regular linear multiple regression. So logistic regression is used when you have one outcome variable that is categorical, but usually binary, like yes or no, and you have sometimes a really high number of independent variables or predictor variables. So in the regression framework, we're usually talking about predicting an outcome from a set of variables. The predictors can be any kind of data. They can be continuous, they can be categorical, but what makes it logistic regression is that your outcome is binary. So when I'm meeting with people and they're describing their research question to me, usually there are some phrases or words that I start to pick up on that start to steer me in this direction of logistic regression. So when people say, I want to create a scoring system, or I want to know, out of all these things, what predicts dying, what predict, whatever it is they're interested in. When they say, I want to know what predicts this, I want to know what causes this, that's when I start to think, okay, they're talking in a regression framework, so let me shut all that other stuff out, all the other techniques out, and kind of figure out how it will fit into a regression technique. So this is one example would be what are the predictors of mortality in elderly trauma patients? And again, I borrowed this from a study that I worked on a few years back of Dr. Bradburn's, and I took a lot out of it. There was a lot. He had some other things going on that I've kind of left out for simplicity's sake, but this would be an example of data and some possible independent or predictor variables that you might look at with such a question. So you have age, gender, their ISS score, and then of course the outcome variable, being their mortality. Frequently, a lot of times people, obviously, especially with regression, they're going to have way more variables than just this. Sometimes we call it, the kitchen sink. This is a kitchen sink project because it's like everything in the kitchen sink. And we kind of try to stay away from that a little bit, but in regression, it's a little more appropriate there than it is in some other things. So there are times when you really don't have a good idea of what causes something or what would predict something. And so you may have, I've had people say, well, I have 20, variables that I want to consider here because I just really don't know. There's no theoretical basis for, what's going on. And so have a lot of things to explore. Which kind of leads me to the next point. Regression should always be considered an exploratory technique in any kind of regression, not just logistic. One regression analysis by itself doesn't confirm anything. You're not gonna, we talk about, we use language like predict, but really just from doing one analysis, we're not at that level of certainty where we can feel like that we know exactly what's going on and what's causing something. So it's an ongoing process. Lots of studies, lots of replication, tweak something here and there before you really can feel confident. So I'm always trying to kind of tell people don't don't hang your hat on everything we find or don't find in a single study, because regression is just not powerful enough to do that in one go around. To talk a little bit about this, and I don't want to jump ahead too far into the power analysis stuff that I want to finish up with, but regression is, just kind of to give you an idea, it's probably one of the most, as far as sample size requirements, it can be one of the highest of different statistical techniques. The other would be if you're looking for something that happens very, very rarely, like a complication that happens 0.5% of the time, and you want to do something to decrease that. That's really hard. I did a power analysis once for somebody and told them they needed 6,000 patients, and that was a no-go. But they were trying to decrease, they were trying to make a small decrease in something that already hardly ever happened. And so it was a nightmare from a sample size perspective. But regression is, it kind of can use as many cases as you can get. My rule of thumb that I like to go by for a minimum sample size is 20 cases per predictor. So if you have 5 independent variables that you want to put in your regression model, then you're going to need at least 100 patients. But that could still not be enough. So that really is a minimum. I always feel more comfortable with 200 or maybe even 150, but definitely 200. But I could do, if you had 1,000, there are even more things I could do that would make it better. So there's really, I've never had to tell anybody, you have too many patients for me to do a regression. That's never happened. It'd be kind of nice if it did. And I'll go into more detail here about why more is better. So again, without going into all of the calculation and I guess I kind of wanted to talk about this more from a conceptual approach, or why you might use it. So you're not going to see, I don't have a lot of like numbers or anything like that here. So this is kind of just an outline of what is involved in a regression analysis. And it's this first point here that is why I say more patients are always better. A few years ago, I went to a SAS. So SAS is the statistical software that I use, and they're a fabulous company actually, and they offer training. They have a lot of training centers around the country and around the world, and I have been up to Rockville a few times to take classes, and so I was in a SAS class for kind of data mining type stuff, and we talked about this concept of a develop data set, a test data set, and a validate data set. And it was the first time I had ever really heard about this. So basically what you can do if you have a large enough amount of data is you take that and randomly divide it up into 2 or 3. You can do without the validate one if you have to. But you divide it up into 2 or 3 sort of random samples. Take your big sample and divide it into 3. And then you use the developed data set to build your regression model. And you basically can just do what you want. You can try things, change things, do a little bit here, say, no, that doesn't work, I'm going to do something else, and just keep tweaking it just to the, because normally in a statistical analysis you say, I'm going to do what I've laid out and I'm going to stop, right? Because if I keep massaging the data, I'm going to get something, and then I'm getting into error and presenting conclusions that maybe aren't real because I did a bunch of analyses that I didn't say I was going to do. This gets around that so that you're developing your model on one set of data, then you test it on a separate clean set of data that you haven't done anything with. And then if you have enough to make that validate data set, you can then do it again on that validate data set and see if the results held up to what you got on your test data set. So this ties back to what I was saying about one regression not being enough to really determine anything. This helps with that. So if you have a large enough sample that you can divide up into 2 or 3 smaller samples to kind of do this best practice method, then you're strengthening your study overall, instead of just saying, well, here's my 100 patients that I developed and tested and did everything to, for this model, and this is what I'm saying. It adds a lot of strength to your study if you can say, well, I've partitioned things this way, and I tweaked my model here, and I tested it, and I validated it, and this is what I'm getting. So that's why I say more is always better. If you have lots of patients, that's great. I can deal with that. So the first step in a regression analysis is always EDA, stands for exploratory data analysis. So that's basically looking at the relationship of each predictor with the outcome variable one at a time, which we would call univariate analysis, because you're just looking at things one at a time instead of all together. And it's basically just descriptive statistics to try to get a handle on your data set, see what you've got, and kind of go into the rest of your analysis with an understanding of the data that you're working with. Then sometimes I will use stepwise regression techniques. If people say, oh, I have 25 variables I want to put in this model, and I have 200 patients, and I'm saying, well, we can't really, that's probably not going to work. So stepwise regression is a somewhat controversial, but I think still, has a place in helping you narrow down from a big number of explanatory variables, predictor variables, to some things that are more likely to really have meaning for your model and for your outcome. So that is something that I do use. There are different ways of doing that, and that adds a little to your write-up because you want to explain that that's what you did. But it can be useful if you have no clue what to expect and you have a lot of variables and you need to kind of narrow down to something a little more workable. And then finally, another piece of regression is the ability to look at interactions. So just like we talked about interactions before with ANOVA, you can have interaction terms in your regression model, and there's a lot to kind of play with there. So regression is definitely much more of like an artistic type of a thing than a chi-square. There's only so much you can do with a 2x2 table. But with the regression, there are a lot of different things you can do, different things to try and tweaks to make, and it takes a little longer to do, but is interesting. Actually, I enjoy it quite a lot. So the results of a logistic regression, you will find out which, if any, of your predictor variables were statistically significant and have a significant effect on the outcome. There are a number of statistics included in the output that tell you about the overall strength of your model or the predictive ability of your model. And one thing that's nice about those is some of them allow you to compare different models to each other. So you might run one model and then run a second, and then if you compare the fit statistics, is what they're called, you can sort of decide which model's better based on that. So that's one angle to regression. And then odds ratios are a really common way of reporting the results of a regression. So if you have a significant predictor variable, you can explain the meaning of that or the results of that by using an odds ratio. So it might be something like, well, I don't know, patients with Staph aureus who have a ID consult are 6.32 times more likely to live compared to patients who don't. So you get that odds that compares kind of one level of a variable to the other. So if you had a variable of receiving an ID consult, some that did and some that didn't, you're comparing what are the odds of the outcome for those two groups, dependent on whether or not they received the consult. And so that's probably the most common way to report and interpret regression results or logistic regression results, and can be useful. And I think, that's something people can grasp. They kind of get the meaning of that easily, and so that makes a nice piece of an interpretation. So again, sorry not to have a lot of numbers or detail, or maybe that's better that way, but hopefully that helps you understand kind of what logistic regression is and when to use it, and sort of what are the things that you can expect from that. So that's a fun one, and one that I see a lot of. What did I say? 60 or 70% of the stuff I do is chi-square and logistic regression. Probably the other remainder is power analysis. So we'll spend a little bit of time on that. That's usually how my relationship with my clients begins, is they contact me and say, I'm doing a study and I need to know how many patients I need in my study, can you tell me? And so then I kind of have to back them up and say, well, can we back up and tell me what your study's about, and send me anything you've written, and let me ask you some questions, and then I'll probably need some information from you, and then we can arrive at that number. So what is statistical power, actually? It is the ability to detect an effect that actually exists. So when you do a power analysis to figure out your sample size, you're trying to make sure that you don't miss something that's really there. Sometimes people ask me, and so power analysis should always be done in the planning stages of your study. I sometimes have people, not too much, but occasionally come and say, I did this analysis, and now could you do a power analysis for me? Because I want to know why it's not significant. And I always tell them no, because I just don't, there's not much wisdom in doing what would be called a post hoc power analysis. It doesn't really do you any good at that point. I've also had people sometimes ask about, after the fact, with a significant result, they might bring up power, and I always tell them no. If your results are significant, then you had enough power. It's only for the case where your results aren't significant and you're wondering why. So if your study is underpowered and your results are not significant, you could be missing being able to find something that really is there. Hopefully, if you did a power analysis ahead of time, then at least you know how much power your study had, and you can make your conclusions accordingly. There are also times when people can't meet the sample size that's needed to have statistical power, but at least they know that going in. And so then I will tell them, if it turns out that your results aren't significant, you're going to need to consider that it's because your sample size was too small. And so by doing that power analysis right off the bat, as soon as you have a research question and kind of start to figure out your study, then you know what you're getting into as you go further. So people sometimes seem intimidated by power analysis, but I always tell them it's a blend of science and art. I use software to do my power analysis, and it's more than just punching in a couple of numbers and spitting out an answer and being done. There's a lot of flexibility. It's a ballpark thing, not an exact thing. And that makes people uncomfortable sometimes. They really don't like having to estimate or guess, but it's okay. It really is okay. So there are a few pieces of information that I need to get from people, or that they need to know before we can do a power analysis. So the first thing is, how will you analyze the data? Because the power analysis is dependent on the statistical technique that you're using to analyze the results. So you have to determine, am I doing a t-test, am I doing an ANOVA, a correlation, whatever. And then, once you know that, then you have to get some estimates usually that fit with that technique. So, I can't remember, So we're gonna talk about this as though we were doing like a 2-sample t-test. So I'll ask people, well, kind of what do you think the mean will be in this group? What do you think the mean will be in that group? And they'll tell me, or we'll say, how small of a difference, because the smaller the difference you're looking for, the more people you need. So how small of a difference would be clinically meaningful to you? At what level of difference would it be big enough that you would change your practice? There are a lot of questions like that, different ways to come at it. The first place to look is in, previously published studies, but oftentimes that's hard. I mean, I've probably done, 200 power analyses in the last 10 years, and maybe 3 times I've had people give me something from literature. Like, it's just not very common to be able to find an estimate that's published that's exactly what you need, because hopefully you're extending knowledge, you're doing something that hasn't been done, so it's tough to find that. So most of the time we end up going with these educated guesses, and it really is okay. It's just about getting in the ballpark, and that's all right. And some people have a level of discomfort with that, but they should let go of it, because it really is okay. So we'll get these estimates of like the means of the 2 groups. I need to know something about the variability in the groups, like how similar all the people are expected to be to one another, if they're all going to be really different or if they're all going to be kind of pretty much the same. And then I can put those numbers into my program and it'll spit out a sample size. But there are other ways. The nice thing about a power calculation is it's, 2 or 3 elements to it, and you can, as long as you can put in 2, you can solve for the 3rd one. So sometimes we come at it in a different way. If people tell me, I'm a student, I have to finish this in 6 months, I'm consenting all these patients myself, I only have this many days to be in clinic, I can only get 50 patients or whatever. Then I can put in 50 and I can say, okay, well, this is how much of a difference you'll be able to detect. If the difference is smaller than that, it won't be significant. You understand that's the trade-off here, and they say yes, and we go ahead. So that's one sort of other way to come at it. And a lot of times, I like to give people multiple scenarios. So because they're kind of uncomfortable with giving me one estimate, they have a hard time narrowing down on exactly what that should be, I'll say, well, if you think there's going to be you're not sure if it's going to be a 5-point difference or a 10-point difference, let's put them both in and see what we get. And we'll kind of talk this through till we arrive at something that you feel comfortable with. So that's kind of how the power analysis process goes. It's not as rigid and sort of scary, I think, as some people think it is at the outset. And thankfully, with having software that does that, it's possible to do a lot of different ways, different approaches, and to do it quickly. So that's a nice aspect. Okay, so this is just sort of a warning, I guess, that if you have research of your own and you're maybe sitting there thinking, well, what I'm doing doesn't fit with anything she said, so what do I do? I'm gonna panic. Don't panic, because it's impossible to cover all of statistics in 2 one-hour talks. So there's plenty more things out there that I didn't discuss. There's plenty of things out there that I don't really know about. Sometimes I have to Google and figure out, well, with this little, this is a little bit different from what I usually see, so what do I do and what do I need to change here to make this work? Don't be afraid to ask for help. We can always work and figure out what the right technique is for the question or the data that you have in mind. These are just some of the things we do. As I said last time, we like to get involved early on. We can help with study design. We can help with how your variables are measured, picking out the right statistical technique. We can help with data collection and data sources, and then of course the analysis and interpretation of results, and then I will help people write method or results sections. I definitely consider that to be part of my job, is how to write up the results of a t-test or whatever, because there is a specific way that that's supposed to be done, and that's part of what I do. I'm not going to go over all these because we're pretty much out of time, but if you get a chance to look at this, these are just some of the questions that we might ask you in a meeting that you could kind of be prepared for ahead of time, and then there's our contact information again.